Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So for today's show, we've got another exciting episode lined up, a very deep technical discussion with Dr. Chris Tighe, who is the founder and managing director of a company called Electrical Cooling Solutions, who are very, very involved in modeling, simulation, design, development, and things like that to do with high-performance motors. So Chris, welcome to the show.
Thanks for having me, Ryan.
And I just wonder if we could start with a bit of a background on you, Chris. How you came to be doing what you're doing now.
Yeah, good question. So I guess it all started when I studied mechanical engineering at the University of Nottingham. So I've got my master's in engineering in 2007. During that undergraduate period, studying mechanical engineering, I found I had a particular interest in thermodynamics, fluid dynamics, and heat transfer, which seemed to be contrary to my fellow students. They like the other subjects, but this is the one that resonated with me the most. As we got to the end, a lot of the people in my course, they were heading off to work, but I think I felt I wanted to pursue further research and understanding on these subjects. So knocked on a few doors to see what PhDs were on offer at the time. And there were two laid out on the table. One was around internal combustion engines, actually. I took a course on IC engines in my fourth year. And the other was on cooling of power electronics on aircraft. At that time, I had very, very little understanding of the electronic and electrical engineering world. So it was kind of an unusual one for me. But I had a chat with Professor Steve Pickering, who was the academic, and kind of got to know more about that topic, which was on managing short, high current spikes for power electronics on aircraft.
Oh, wow, yeah.
Such as lightning strikes and overcurrents. And that sounded pretty interesting. I like
nothing trivial.
So I kind of went, nothing trivial at all. No pressure.
Yeah.
So I chose that, and actually, with thinking about it, the IC engines and this topic that took me into the electronics and electrical engineering world, and how pivotal a decision that was in my life, given where I am now. It's quite interesting to think back how these two technologies have taken a very different route since. Maybe they would have converged back at this point somehow with the IC engines and adopting electric technology.
Yeah.
So that then went on to do a PhD for 4 years. So that was on really modelling heat transfer within power electronics.
Okay.
And as I said, these are very, very short transients. And what became apparent at the time is 100 milliseconds is an eternity in the electrical engineering world. So current can come and go. But from a thermal point of view, this is a long, long time.
Yeah.
But for electronics, it's
electrons move quite quickly. Yeah.
A lot of things can happen in 100 milliseconds.
Yeah.
But from a thermal point of view, if we think about a typical stack from a power electronics, you've got the device and a substrate underneath, and then typically a base plate, and underneath you have conventional cooling, liquid cooling.
Yeah.
But it takes more than 10 milliseconds for the heat to get from that device to the liquid cooling.
Yeah.
So if you've got a 10 millisecond pulse, that coolant's doing nothing to help reduce the temperature of the device within that time. So you have to think about some other needs. And we were looking at putting heat reservoirs, because it's not quite a heat sink, heat reservoir right on top of the device. So as this heat is generated in a very small time, it kind of gets dissipated into this heat sink, or heat reservoir, as I've called it. It's held there until the pulse is over, and then it dissipates back down to the liquid cooling. So you're just trying to store that heat for while we see this lightning strike or overcurrent fault, and the electronics decide whether it's a lightning strike and we just have to ride through it, or whether something's broken and we need to switch off.
Yeah.
So that was quite interesting, and that's where really I started modelling heat transfer. So we looked at some of the commercial software available, and given the nature of the topic, we kind of need to model transient thermal conduction down to sort of 1 microsecond level, just to see how that heat dissipates in very small electrical engineering sort of timeframes.
Yeah.
We also have anisotropic conductivities with different materials that we were looking at to see how beneficial that was. We have tried to simulate the losses, which are temperature dependent, depending on how the resistance. So there's a lot of complex things that's going on, and none of the commercial software at the time we felt was suitable for doing this. So that's where I started coding as well. So developing these thermal solvers to be able to model niche things like this. So this is a very, very niche topic that we were looking at, but it gave me a good understanding and different transient solving schemes and implementing code that's then used to actually generate results and do some proper engineering analysis of a thermal problem.
And that is, often with colleagues in the past, we talk about sort of design of e-machines and power electronics for automotive applications in particular is a thermal problem. Often solving the thermal challenges kind of dominates and drives a lot of activity and behavior and component specification, and an awful lot of what you do is all about managing heat and heat flows within the device and controlling all of that to within an acceptable level. So it's a key part. It's interesting how you kind of came into that juncture, because typically it would be seen as being very separate. Sort of the mechanical engineers at one side of the building and the electronics guys at the other. So were you getting sort of a good insight into how power electronics modules were being built and the sort of challenges and issues that were coming about all the way back then?
Definitely. I spent a bit of my time, I suppose, more on a device level, looking at how MOSFETs and IGBTs worked with the different gates and the draining of the source. I'm still no expert, you can tell, but really looking at it from a device point of view. So where you've got this tiny device which is only sort of, I don't know, 10 mil by 10 mil and maybe a mil thick, but actually you want to know exactly where in that device the heat's being generated. Is it evenly distributed, or is it just in the top slither by the drain of the source? For most problems, that's completely irrelevant if you're looking at steady state. But when you're looking at what happens in that first 10 microseconds or 100 microseconds of a heat pulse, that's critical to see how because it's dissipating just within the device itself at that time, and then it goes through either down to the substrate or in different directions.
But that's an interest. I mean, that you sort of summarised there. One of the challenges I always had, back in the day when we were sort of doing early work in electrification, was trying to get people to think about things as non-steady state, because an awful lot of our industry was all about modelling things at a steady state condition, and even sort of a lot of so-called transient models were effectively a chain of steady state models stuck together, and it didn't really show you a true transient condition. But for a driveline application, it is transient. I mean, it's almost never in a steady state condition. Even when people think it's steady state, it really isn't steady state, because things change all the time. But so driveline applications are highly, highly transient. Probably not as transient as a lightning strike, I would guess, but still quite a transient application. So a good sort of start. So then you did your PhD. What happened to you after that?
So PhD was on power electronics. I went to work at Cummins Generator Technology, so a big global company. But at the time, they had a big CGT, as we call it. The plant was in Stamford, so they had the engineering office as well as a lot of manufacturing capability within in Stamford. So I went to work there within this company as a thermal engineer, and that was really about developing thermal engineering capability across the global sites. So that the main hub of the engineering world for the generator arm of Cummins was based in Stamford. But at this time, you could really see that thermal engineering was starting to be taken seriously. If you look at the work that they'd done previously as a company, Newages before it was Cummins, very little was paid attention had been paid to thermal. It was kind of an afterthought.
Yeah.
Put a bigger fan on it. If it's running too hard.
Yeah, there's big. I think so. A lot of people would know Cummins obviously for engines. Maybe some don't realize. Ironically, they changed that division quite heavily just as they were going into electrification on the other side of the business. But they had a big competency in electrical machine design and manufacture in the UK for generator sets. But like you say, a typical gen set, power density is not all that important. They're quite large machines. They're sort of air cooled and quite different to what you would find in a traction application. What sort of things were you trying to do there in terms of thermal optimization in that kind of equipment?
Sure, exactly. So these are through flow air cooled generators. So we've got a fan on the end that's pulling the air through, and really we're looking at new product development and product improvement. So some of these designs electromagnetically developed back in the 70s and mechanically not changed a lot since. And these things are designed to last a certain number of years, about 20 years. So we're kind of getting to the point where you're starting to understand what the real lifetime of these machines are.
Yeah.
So a lot of it is kind of, okay, we have this standard product. How can we improve it? How can we get a bit more lifetime? But also looking at efficiency. So, and a lot of the applications of these generators were for off-grid, either diesel or coupled to a diesel or gas engine.
Yeah.
So where, in remote areas in parts of the world where they're running 24/7, providing just a constant power. And they're coupled to an engine which is burning diesel or gas. And so if you're looking for just small efficiency gains, a 0.1% efficiency gain, depending on the size of the generator, equates to sort of thousands of litres of fuel saving over a year.
Yeah.
Now, customers looking at that from a financial point of view, with the price of, especially the volatile prices. So they want to save money on fuel, but also from an environmental reason, just burning less fuel, it's a significant saving. So, and 0.1% doesn't sound like a lot, but these bigger generators, they might be running at 90, 96, 97% efficiency already.
Yeah.
So 0.1% saving is relatively significant. And that a lot comes down to thermal. So if you can put a better thermal cooling system on, if you can improve the cooling system whilst running at the same power output, you're running at a lower temperature. And if the temperature is lower, your electrical resistance is lower, so you're generating fewer losses because of these are ohmic losses, which are the main heat dissipation within these types of generators. So if you can do that, but also we talk about fans as well. Okay. These things are fan powered.
Just wondering that.
We understand
reducing the fan power. Yeah.
Exactly. So if you can bring that down, so the fan affinity laws, which gives us good engineering rules of thumb about how to design a fan. The ratio of the diameter of the fan is proportional to airflow rate to the power of 3, but it's also proportional to power to the power of 5.
Yeah.
So I think if you increase your fan diameter by 16%, you're almost doubling the windage losses on that fan. So if you can optimize that fan, reduce the diameter, get it pulling the same amount of airflow through, or in many cases, a lot of that air that's being pulled through the generator is not doing much cooling at all. It's going through big passages on the outside. It's not picking up too much heat. So you can reduce the total airflow through the machine and having a much more efficient fan. That reduces the windage losses, which is another component of your efficiency.
Yeah. Oh, okay. It's fascinating. So, and then did you go straight from Cummins to setting up your own business, or how did you come about? That's because it's a pretty big leap to take from a global company like Cummins to.
Yeah. So 2 years at Cummins felt lucky enough. I think it had very much had the feel of a big American corporate company, and some people thrive in that environment. But I think I like to work in a more siloed environment, I suppose, and then have a bit more freedom in terms of what we're doing. So we did a lot of work on thermal modeling in Cummins as well. And again, some of the commercial software was not ideal for what we wanted to do, particularly if we wanted to be innovative. We needed something where we could do some thermal modeling and quick thermal predictions more easily and incorporate innovative features. So a lot of the work I did there was developing their in-house, they're still using today, their thermal resistance tool for predicting temperatures. So I had a good grounding at that point for simulation using CFD as well for predicting airflow. So from there, I kind of took two almost parallel strands. I went back to the University of Nottingham as a researcher. So this is 2013. But at the same time, after making a couple of connections at CGT, kind of started Electrical Cooling Solutions, ECS. So I think technically it was incorporated at the end of 2012. But at that point, it was just kind of a bit of work that I was doing on the side, whilst most of my work was actually as a researcher at the University of Nottingham.
Right. So tell us about Electrical Cooling Solutions and what you do now, because it's obviously...
Yeah.
I was looking at my watch to try and work out the number of years in my head there. That was a bit stupid of me, but 22 minus 12 is 10. I can do that maths just about. So yeah, go on.
So 10 years, but really I started operating ECS full time in 2018. So technically, I think of it as a 3.5-year-old company now, rather than a 10 years, which probably suits the maturity of the company a little bit better. So we specialize in thermal computer simulations, modeling, and applying analytical techniques for electric drives. So we design and optimize thermal management solutions for motors and generators, which we've discussed, power electronics and power converters as well, and also batteries. So anything that incorporates an electric drive system, which is sort of power hungry and generates a lot of heat. And we also look at the system integration of all of these things together. So some of our work is improving the thermal performance of hardware which is already on the market. That might be resolving thermal issues or improving performance to make that product more competitive in the marketplace as newer products come on, which are on paper better specifications. But we also do a lot of research and analysis of advanced cooling methods for high performance and breakthrough technology products as well. So still doing some work with the University of Nottingham, which is more on an R&D level. But fundamentally, we do specialize in simulation and modeling side of thermal engineering.
And you do that as a sort of service? So someone would come to you with a particular problem, and what's your approach?
Absolutely. So people come to us sometimes, often with a problem, more often than not, which perhaps underlies the problem from 10 or 20 years ago in the way that thermal management was considered within the industry. But yeah, come with a problem, or often come with a design project as well, saying we want to develop this new product. The number of thermal engineers on the market and available in the electric drives industry, and this is one of another underlying problem. The number of people with really, let's say, formal training and have a good, solid understanding are probably not sufficient compared to the demand, the number of companies that are developing. So a lot of the time there are mechanical engineers and electromagnetic engineers running thermal simulations.
Yeah.
And that's great, and the industry needs this, but sometimes they need a validation check, or they need somebody with a bit more experience to come in and do some modeling for them. So yeah, often, or more often than not, it's someone with a new development project. They need someone to come in and do some thermal calculations, predictions. How hot is our product going to run?
Yeah.
How can we reduce the temperature? How can we get more power out of this? How can we, we want to remove some cost from this existing product. Generally, people want to take copper out, because it's expensive. So, but obviously not wanting to reduce the power output. So a myriad of problems as well. And sometimes there's a high performance and innovative products that are coming where maybe there's not a product on the market which is quite operating to the power density that they want, for example. So it's not really a copy paste of an existing product. They've got to think a little bit outside the box, and first and foremost, you've got to make sure the thermal is working, because if you don't, your product won't last long.
Yeah, I had a few of those in the past. The working and not working varieties. So is that predominantly then electrical machines, or are you also is it power electronics as well, or other? I mean, are you doing other things, or are you predominantly e-machine?
Predominantly, e-machines is what we work with. That's where our existing network is perhaps strongest.
Right.
We do power electronics with products as well, and a lot where it meets in the middle. Integrated drives are a common theme now. So instead of having a separate drive unit, sticking the power electronics in or around the motor and trying to have a single package, that is great, but it does uncover a lot of thermal issues because you're trying to cool the same amount of heat in a much smaller packaging. So they do meet in the middle. And more recently is where we're doing battery thermal management, which is another topic which is highly important, especially with e-motors and the EV sector. Battery is one of the technologies which is developing technologically probably quicker than the motors or the drives.
Yeah. And batteries are typically especially fussy, the Goldilocks effect. Motors are quite nice in that sense because they don't really mind being cold. The colder the better, and your electronics.
Right.
But batteries don't really like being cold and don't want to be hot. I was doing something the other day where they were talking about cooling in battery packs. I was like, really isn't cooling. It's thermal management.
Management.
Because being cold is as much of a problem as being too hot. And so just to sort of dive a little bit deeper, because in my head, obviously a lot of simulation tools out there, like you can do, machine drive simulation, electromagnetic simulation, and a big part of the standard tools out there is the thermal sort of characterization of what's happening in your electromagnetic system. So how does what you do differ from that? So if someone's sitting at their desk and they're using one of those standard design tools, there's a couple out there. You get those thermals and those heat maps and stuff. And what do you do differently?
Yeah, that's a really good question. So there are different degrees of, let's say, resolution which you can conduct thermal analysis. A lot of these tools are doing maybe the lowest end. They want to produce a thermal calculation very quickly, so they're using something like a lump parameter or thermal resistance model with perhaps not so many nodes, and each node represents a certain part of the motor. So you're predicting temperatures at maybe 20 locations also within the motor, which is good to give you a good idea. But underlying these calculations are a lot of assumptions. And understanding what assumptions are being made in your thermal calculation is highly important. Some of the packages give you options to go in and tune them, but that requires you to understand what values to put in, what assumptions. If you're going to override the defaults, you need to have a better idea of a value to change. One common example is the heat transfer coefficient. So any interaction with a solid, with a conduction area, so that's the motor, with any liquid cooling or air cooling. Air and liquid, very complex to predict. So we use CFD for that, but CFD takes a long time. So these calculations assume a heat transfer coefficient. So assume how well that surface is being cooled, that body is being cooled, and the liquid. And they're using underlying correlations most of the time. Some of these correlations were developed, actually some of them as long as goes to 1920s, I think. Certainly, I think the 1950s and 60s, there were a lot of work done. They're still being used today, even though if you look at the speed of operation, so high-speed machines, small diameter, different things, they're not necessarily applicable. So they're very good for getting a good idea of, whether you're 300 degrees or 100 degrees, if you're on that right ballpark. But that's really all they're good for.
Right.
You can't be too confident with these tools to the exact degree. So you probably got quite a large margin of error. Good for cooling concepts. So we have our own thermal resistance tool that we've developed in-house. We have our own tool because we were able to incorporate clever design features. So if we're we want to simulate or model a particular type of cooling, if it's a new air channel through a state or a type of vent or something, just anything innovative, we can then incorporate that. But I suppose inherently, if there's a drop-down option or a tick box in a piece of commercial software to model some sort of cooling, then inherently it's not innovative because someone's thought of it before, and anyone with the software can model it. Yeah. So that's one key difference. We also do a lot of CFD, and CFD is really important if you want to make thermal predictions more accurately, because that's where you start to simulate the air, whether it's internal air or air cooled. For example, in the example of the generators, how the air is passing through the generator, or an aerospace machine, if you've got direct liquid cooling, so you're pushing oil or through the machine that's in direct contact with the windings and going through the status lock. You need to simulate that in quite a lot of detail, because the heat transfer coefficient is varying a lot within the machine. So depending on where the turbulence is occurring, so you need to model that directly to get good temperature predictions out, and that's where CFD comes in. And CFD, it's been around a long time. Obviously, there are many commercial packages that you can do it. We find this is where one of the biggest technical barriers come for normal companies, because setting up a CFD model is non-trivial. You really need to understand how to set your model up, what sort of mesh to apply. Is very, very fussy with respect to the mesh that you put in. Yeah. Unlike something like mechanical or electromagnetic, where you kind of just chuck a mesh in and it works. The mesh for CFD needs to be very specific. And then also the settings. So do you need a compressible or an incompressible cell, or what turbulence model to run? Is my solution converged? CFD will always generally give you an answer, but to know that you've got the right answer requires a lot of the knowledge.
So you're doing like these sort of really detailed coupled models, and I guess, is this sort of going back to almost the earlier point where older electrical machine sort of development, industrial electrical machines, they weren't all that power dense and had a lot of thermal mass in the machine anyway, and and efficiencies were in a different place to where they are now. So now we're doing mobile applications, so power density is everything, and super cost. There's huge volumes, lot of cost optimization work. So we're trying to squeeze every last cent out of it and every last watt of performance into it. Is it that kind of, because we're in that real sort of into that much higher performance regime for machines, that it's all becoming much more critical?
I think that's exactly right. As you want to provide cooling, so direct cooling, you really need to look at this on a much more detailed level. I suppose going back, and as you were saying, I was thinking back in the 70s, they didn't have CFD, or they had it on a very basic level. And certainly you couldn't run a proper CFD model purely because of the computational power available. I think when I started at Cummins, as an example, so that was 2011, we could run CFD meshes going up to maybe 10 million cells, which isn't a huge amount if you're trying to simulate a generator. Very true. So you have to really, let's say, you need to budget your mesh. You need to be really strict about where you're putting cells. Now we're running CFD within the company, so we're operating on the cloud. We're running sort of 200, 300 million cell meshes without really thinking about it.
Wow, okay.
So certainly computational power is no longer an issue. For a long time, particularly the early part of my career, that's where it was an issue. I suppose as of a few years ago, particularly as technologies and CFD, you can start running it on the cloud, your computational power is almost infinite, which does open the door to be able to run these CFD models in a lot more detail.
Yeah.
And maybe that's perhaps driving the demand from the industry to, as you say, squeeze every watt out. It's without these tools available, we'd find it very difficult to do. It would certainly be done on an experimental basis, which becomes then cost and time inefficient.
And actually, I mean, we have this debate. The experimental basis for machines in particular is quite limited, actually, when you start getting into it, because there's some things that are just very, very hard to measure on a running machine, and instrumenting up a motor is not as easy as you might think, because there's all the noise and things like that to deal with. Obviously, rotating part as well. So, getting some of the measurements, it's like some parts of a motor. People are just, it's sort of, it's like the other side of the universe. We kind of think we know what's happening in there, but no one's ever seen it. So
no, exactly. And temperature varies a lot within the motor. So even if you do stick some devices in, you never really know whether you're measuring the hottest part. You think you're okay, but you could be 10 millimeters away from a part that's even hotter. And sometimes putting these devices in, for example, in the slot, if you're trying to pack that slot out and get the highest slot fill factor, you probably don't have room for an RTD or a thermocouple to be stuck in with the extra cabling that goes in. And even then, you're kind of affecting the thermal performance. So there's some validation that can be done, but it is limited.
So what are then you obviously you can't talk in specifics about customer projects and stuff, and I get that, and I'm sure everyone will, but in general, what kind of trends are you seeing? You must be right at the cutting edge of, Chris only gets called when we have a big thermofluids problem on an e-machine. Yeah. What would you say the key trends are that you're seeing in the market?
Key trends. I suppose direct liquid cooling is becoming incredibly more common, and really that's what you have to do if you want to get high power density out of the machine. So instead of having a water jacket, which is quite common in the EV world, where you have just around the frame, you've got some coolant that's flowing. The heat then still needs to conduct from inside the slot through the stator core to the coolants. So thermally, that's quite a big path. And a lot of the thermal resistance in an electric motor is within the slot itself, because you've got all your conductors in there, but you've actually got quite a lot of insulation, electrical insulation. So the slot wall liner, some resin inside the slot. So the radial thermal conductivity might only be 1 or 2 watts per meter Kelvin, whereas bulk copper is about 380.
Wow! So
you've really got quite a big thermal resistance just to get out of the slot and then through the stator back and then to the coolant. So for any super high power application, you've really got to get that coolant to the windings itself. So putting cooling channels in the slots itself. So whether that could be air, that could be liquid.
Yeah.
Of course, you have to be careful about dielectric. Liquids and what you're putting through there. You don't want to be sticking water through there, or else you get a shock, literally.
Yeah.
So getting the cooling to there. So, and that can be quite tricky to do. There's a lot of manufacturing issues. We see that on high performance EV electric vehicles as well, but particularly in aerospace.
There's
another trend in it.
Go on, sorry.
No, I was going to say another trend in aerospace is actually going full circle and saying, okay, well, can we air cool our aerospace machine? Because actually it's a lot more reliable than relying on a liquid cooling circuit, which can be prone to failing.
Oh, till it sucks in a seagull and...
Well, there is that.
Yeah, icing. The icing inside the machine is a interesting phenomena to deal with. I was going to say, so on direct liquid cooling, so something see about. There's a couple of different approaches, and you mentioned sort of dielectric. So dielectric oil spray inside the machine on directed sprays onto the end windings, or a sort of immersion kind of bath type system, or even people passing dielectric through the windings themselves. Do you see a particular trend there, or is do you think there's one method that's better than the other?
There are certainly different methods that are easier to model. Let's put it that way. Okay. So the through cooling, if you've got something completely flooded and it's just a single volume, single fluid. So if you're passing liquid through, for example, that's quite easy to simulate. Spray cooling, we do see that it's been around for a while, but people have not really understood how well it's cooling a machine, because you've got two phases. You're spraying it, which has a cooling effect. You've then got some sort of thin film of this fluid on the stator, or on the rotor, which is then absorbing some heat. Then you've got the evaporation. So there's which again that's very good at cooling. So spray cooling is common. A lot of the prior work that's been done on it is kind of experimental based, just to understand what can be done, because a CFD is very difficult to do with the two phases. But we do see that being used quite a lot. I think immersion is less so unless you've got that two phase, unless it's actually evaporating the liquid. It's really just relying on natural convection, so much better to pass the liquid through and then get some forced cooling.
Right. And then if you're passing, even fairly low viscosity dielectric fluid through a machine, you must start to get some quite complicated things going on in the air gap with sort of, because typically a higher performing machine, you would have tighter and tighter air gap. So what starts to happen in the air gap, and does some of that offset some of the benefits you might get elsewhere?
There are different ways to do the through cooling, and one of the common ways is actually to separate the rotor from the stator, so keep the rotor completely dry, which is useful if you're using permanent magnets or a non-magnetic, non-permanent magnetic rotor, where the cooling is perhaps less critical, and then just pass the liquid through the stator. So that usually has a carbon sleeve that passes through the air gap. It has to be quite thin. As you say, air gaps, these machines can be quite tiny. So separating them is the easy way to do it. If you flood the entire machine, the rotor and the stator, we can pass it through, but you start to get windage, an additional windage, because the rotor's spinning, and instead of just rotating against air, it's then got to, the high viscosity of the liquid creates higher windage. So that's not often ideal. So typically these applications do see where it's fully flooded, where it's just the stator. For the spray cooling, it's far more open. And I think I read that if you flood the rotor to a certain level, which is maybe only 10 or 20%, it has very little effect on the windage loss, because the oil gets kind of dissipated throughout the air gap and it doesn't affect it too much. The more that you flood the machine, the more that starts to have an impact. So I think completely flooding the machine is not ideal, and I'm not sure I've seen an application where that's done.
I've seen one like that.
Okay.
Yeah, and in some applications, if you're dealing with really high pressures, to pressure compensate the motor, you end up having to completely flood it, which is, like you say, that's very difficult. It makes it tricky, but it's better than the alternative. So, yeah, okay. And then obviously we talked there a lot about the stator and the air gap and whatnot, but in terms of rotor cooling, do you get involved much in terms of looking at sort of thermal simulation on the rotor itself? And is there anything interesting you see with rotor cooling?
Yeah, there's a few bits going on with the rotor, and really it depends on what motor technology or architecture you're using. So field wound rotor, where you have got conductors and you're passing current through the rotor to create the magnetic field, you have to treat that very much in the same way as the stator. You've got a very strict thermal limit. That's where beyond that your insulation starts to break down and you get faults. Generally, for the higher power applications, that's not preferred. Perhaps for this reason. Yeah, it's very difficult to cool a rotor with liquid directly. Power permanent magnets, they are still temperature fussy. You get them too hot, they can demagnetize. Temperature limit is certainly higher than it would be for the copper wound equivalent. But then there are other technologies like switch reluctance machines, which are completely magnetic free. And in these cases, you don't need to worry about cooling. Induction as well. You've just got your copper bars going through there. There's less cooling that's needed on the rotor in that case. So some of the technologies, spray cooling, is often used on for the higher power applications. This is on these machines. Heat pipes used inside the shaft is a clever way of trying to draw the machine out. But if you consider just a standard EV machine, which has got the external water jacket, you're kind of just relying on the heat being dissipated to the air inside the motor and then to the casing to be cooled.
I have seen, I mean, it's been a big thing where people are starting to try and have internal liquid cooling in the rotor, and there's a number of good examples on that. There's some lovely animations of some of the Audi machines out there where they show their rotor cooling. Heat pipes is an interesting one where I'd sort of my ignorance on a heat pipe, but I'd sort of always assumed that a heat pipe would struggle in terms of getting the flow in a heat pipe with all of the centrifugal forces going on, that actually it would sort of not work properly. But so you can actually embed a heat pipe in a rotor and it'll function.
Yeah, it does, and I think that's probably because centrifugally it's going to act on the liquid more than the vapor aspect. So you've got the liquid going one way and the air going the other, and the liquid wants to go around on the outside of the heat pipe, which is where you have the wick inside. So I suppose it's flinging out that way, and it just needs to get from the hot region to just a very well cooled cold region. And as long as you've got a big enough temperature difference, that force overcomes the viscosity effects.
Yeah. Okay. Interesting. Because it's rotor cooling, shaft cooling is easier than rotor cooling, and getting you tend to have a big thermal mass in the shaft anyway, even if you aren't passing liquid through it. So anything that can get heat away from your magnets and your air gap and down into the shaft could be a good thing to try and cool the machine better. So okay, so really interesting. So your sort of big trends then really be around looking at more intricate direct cooling mechanisms and more sort of advanced simulation methods inside the machines, and doing the coupled simulation work. So then, kind of looking forwards, I know you've got a few exciting developments happening in your business where you're sort of getting involved in some new areas and launching some products and things like that even. So what are you kind of excited about moving forwards?
Yeah, there is a lot keeping us busy at the moment, which is really good. We're learning a lot from the consultancy projects that we have been doing, the design services we're doing. So if we take one step back just to lay the foundation of what's coming forward, a lot of the CFD work we do, in fact, most of the simulation work that we do is not using commercial packages.
Yeah.
There's a few strategic reasons why we do that. The cost of them is certainly one of them, or originally one of the motivations. But we find creating our own proprietary solvers for things like the thermal modeling tool, or for FEA and the CFD, we're using customized versions of open source solvers. So one of the big ones, the one that we're using for CFDs, is OpenFOAM, which has been utilized and harnessed by a lot of the big engineering companies. So Audi, BMW are big into using this. It's actually used by all of the Formula One teams for doing their aerodynamic studies. So it's a very mature solver, technically equivalent to the commercial packages. But we decided to use it because it's not a black box. We can customize it. It's highly automatable, so we can set for particular applications. If we're doing a lot of electric motors, a lot of rotating machinery, we have scripts, or we know how to set up a model using that, and we can set up maybe 5 or 10 variations of a particular problem with just a few changes, and do parameterized study on that. And we can just set those up to go. They run on our cloud computing, and we can get the results back very quickly.
Right.
And that scalability you can't get with commercial CFD unless you pay for the licenses to run it on lots and lots of different cores. You can't restrict it to. Yeah.
And the open stuff, though, I mean, I've looked at that in the past, and I mean, it's not for the faint-hearted. It doesn't have it's expert system level, basically.
It is, yeah. There's generally quite a high barrier to get to, technical barrier, knowledge barrier, let's say, to get to use it. So I think
Can't just dip in and out.
Typically run through Linux, for example, but that's not to put people off. A lot of these companies are coming over that, but yeah, it's not a case of downloading it and running a CFD model. You certainly need to certainly understand CFD and know what you're doing, and have the time to make sure to set it up and run it according to your specific needs. So from that point of view, it's the same as running something on one of the commercial packages. You still need to know how to set up that CFD model. And then I suppose coming back to the simulations, one of the things that we're doing at the moment is we're creating some new simulation software. Having used the open source and our proprietary tools for some time now, and speaking to industries, a lot of the people that we speak to in industry share kind of similar, almost frustrations, but acknowledge certain barriers to using simulation. I think everybody knows that to get, certainly for these higher power densities, to get the most out of a development project, you need to use a lot of simulation, or simulation is really at the heart of it. So trying different configurations, different cooling methods, things like that. But there are barriers to using simulations that exist. And it seems it's more in the thermal and the CFD world compared to the electromagnetic and the mechanical world. So these barriers are things like cost. So the initial outlay of the CFD license. So if you're quite a small company, thought of having to outlay, $100,000 or so on some software that you're not quite sure how to use, can be quite daunting. It's a bit of a leap of faith. There's the hardware that you need, as I was saying. If you want to run these CFD simulations in quite detail, you can't do that certainly can't do it on a laptop. You're not going to do it on
you're talking
on a desktop.
multi-core not even workstation. It is sort of server-based dynamic processing. I think a lot of people don't realize that obviously, there's a huge amount of skill involved in these things, but actually then the cost of the hardware that you need, the software that you need, and you I think, just in case anyone missed it, it can be hundreds of thousands of pounds. It's not trivial at all. These kind of setups. So the amount of value that sits in doing these kind of very detailed simulations, you've got to be serious to want to do it, and to have that capability in house is out of reach of an awful lot of people, which I guess is where you guys would come in as a service.
Absolutely, yeah. So those really the financial and the hardware barriers. So how do you really want to spend £200,000, for example, before you've got a single simulation result? Not many people want to do that. It's a big leap of faith. And even when they've got it, these simulation packages, do they know how to use it? Do they have the right know-how, so the best practices, to know how to analyze the results? And how do they choose which software and what approach to take? Yeah. And sometimes that leads to some companies having bad experiences in using software where they think they've got a good design, they've gone and tested it, and it does not behave in real life as the software led them to believe. So that means they've lost time and investment and some faith in the simulation process. So the simulation platform that we're developing is trying to really at the heart address these issues. We kind of have this affordability, this accessibility, and this automation at the heart of what we're trying to do. And so our platform, which is called Cohere, it's unlike most simulation platforms. Yeah, that's Cohere. It's a web-based platform which tackles one of the accessibility issues. So you don't need to download and install software to your computer. You can access it from a laptop just through a web browser. And also means if you're half the week working from home, half the week in the office, you're not worried about having to make sure your remote desktop connection is working to get back into the office. And if it falls out, then you've got to find something else to do for that time. Yeah. So and it also reduces the IT requirements on within organizations, and you can easily share design files as well. So multiple users can access same design files. We have cloud computing for the simulation, so that addresses the hardware issue. So you don't need to worry about spending capital expenditure on something that can solve your CFD models, for example. You can just click go when you've got something ready, and off it goes to the cloud. And we build it around workflow templates. So at the moment, we're just addressing electric machines, electric motors. We have aspiration to introduce power converters and then drives and batteries into it at some point, but we're focusing on motors. And by reducing, let's say, the application that we're trying to do, we can automate a lot of what's going on. So from a CFD point of view, for example, we know what sort of settings to apply depending on the size of the motor. We can set up the right turbulence model. We can put the right boundary conditions in. So we know a lot of these problems already. And for different types of cooling, different types of applications, we can create different workflows. So someone coming in doesn't need to be an expert in setting up a CFD model. They just need to say, okay, well, this is what I want to model. We automate a lot of that process there for their ongoing forwards. And underneath, we are using this open phone, which means we can customize it to electric motor specifically. We don't have the licensing overheads that we need to pass on to customers, and it's very scalable as well. So we don't need to worry about having licenses for each user and the number of cores that we're running this on.
So you're sort of bringing the expert end simulation software to making it more accessible for a wider audience, and both from a usability point of view with your workflows and things, but also from a cost point of view, because you've got a more dynamic pricing model than just everything's up front, and it's almost like pay as you go basically for
precisely.
The bigger the simulations you're running, the more work you do, the more you'll pay. But if you didn't have to use it for a couple of months, then you wouldn't. Or maybe not as much.
Yeah, that's exactly right. And that suits a lot of companies, smaller companies who have a development cycle. They may be wanting to use simulation very intensely for, let's say, a 6-month period. And as they go into the manufacturing prototyping phase, that dies off. And once they've got some test results, they want to test it again. So, yeah, the amount that they're using simulation throughout the year varies very wildly. So they just want to, when they want to use it, pay for what they need at the time.
Okay, yeah. And this is is Cohere launched then as a product? So can people go and subscribe to this, or are you about to launch it, or what's the status?
It's very close. So actually, there's going to be 3 simulation models. We've talked about thermal resistance model, which is the more reduced. It makes assumptions on cooling, but it's still an incredibly useful tool. So that's going to be released in March 2012. That will be available then
March 22
later in the year. Yeah, March 2012. Thanks for the correction.
March 22. Yeah, sorry. It's
good,
but it's not that good, right?
Yeah. We'll be releasing that in March 2022.
Yeah.
We have the 3D thermal FEA, which adds a bit of accuracy and detail. That will be released in the next few months as well. And then the computational fluid dynamics, which is the real key bit, that will be slightly later in the year as well. So we're releasing the technology, I suppose, in complexity order. So if you go to the website Cohere-sim, you can click to be notified on updates and as we're releasing things, and let us know if you're interested in having a demo or seeing what the platform's all about. So just follow the link to cohere-sim.com.
I'll put some links in the show notes for people, so that, regular listeners will know that there are notes that go with the episodes. That I'll put a link to your LinkedIn profile, so people can connect with you directly. The company website for both companies, then people can do that and a bit of blurb. So. That's been brilliant, Chris. Thank you so much for taking the time out. I've noticed that's all we've got time for today, basically. So we'll kind of bring it to an end there. But that's been absolutely fantastic. Thank you.
Wonderful. No, it's been really good to talk to you, Ryan.
I think we probably could have done another few hours on thermal simulation and fluidic simulation in machines. It's such a big topic, isn't it?
Absolutely. Maybe offline.
Yeah.